Right, this screencast continues our work on using matrices to solve uh, probability questions. And so what you see on the screen now is where we pick things up really, and that is, let's say our probability is, we're looking at the probability of G across our top line, the probability of G. So this is our transition matrix here in the middle. This 2 by 2 is our transition matrix, and just to recap what that is, we fill our top left with the probability that we have G followed by G. So if G is our subject, is our focus, then this is G follows G. Now remember, this is a transition matrix. Transition means from one to the next. So we're concentrating here on probabilities that follow events. So and the probabilities don't change. That's why we can use this power of n, and we'll come to that in a moment. Okay, so the probability that G follows G fills this spot here, and the probability that G follows not G fills this spot. We sum down to 1, so once we've got those two in place, we sum down to 1, and then we multiply by what's called our first attempt, or our starting, it's our step 0, our starting matrix, which is a 2 by 1. So this is the probability of G and the probability of not G as an initial value, and we're given that information, and the result is the probability of G and not G for the successive events. So if it was on the next day or the next attempt or whatever it is, then this would just be power 1, and then and we'd run this matrix through, and we could probably do that manually quite quickly, but all this can be done on the calculator. As soon as we start to raise this power to higher integers, then we look to the calculator to help us out. So this is where we're at. We're just going to, so I'm just sort of scrolling through these notes and picking up on some themes that we talked about in our last lesson. Okay, so in this example, excuse me, the probability of G follows G is 3/5, that G follows not G is 1/3, and the starting probabilities there is a half each, transition matrix in the middle. We then had a look in this example that if this was a goal is scored on the 6th attempt, then and this was the first attempt, so the 6th attempt would be power 5, and that's how that problem went. We then had a look at so our transition matrix times this was our Friday matrix for probability of snow, I think it was. And this is our Saturday result if we raise this to the power of 1. So if this is Friday's, and this is the next day's result, and that was our answer there. If we looked at the following Wednesday, then we just had to count through. Sunday would have been power 2, Monday power 3, Tuesday power 4, Wednesday power 5. So we take the transition matrix to the power of 5. Our initial values stay the same, and our probabilities change there. So now we're moving into the territory of what's called a Markov chain, and that is when we really just start to look at what the transition matrix and what power it goes to, and we sort of refine that work a little bit. And there was another example there from 11C, I think, and question 7 was for homework. So if we now move into so what we call what are known as Markov chains, you don't need to know too much about this fellow Markov, other than he was a Russian mathematician, and the conditional probabilities, that the transition matrix is what he spent a lot of time on. So and successive powers of those are what's called a Markov chain. And so what we're going to do is look at, and it just sort of refines and focuses our work really on that transition matrix and its power, depending on how far into the future we're looking. So what the Markov chain works with is Sn equals t to the power of n times S naught, and I'll write some notes on what each of these things mean. So an Sn is an m by 1 matrix, which describing the state describing the state at step n. S0 is also an m by 1 matrix. That means m rows, 1 column. M by 1 matrix describing state. This is the initial state. Describing state at step 0. So step 0 is the initial state. And T we know to be our transition matrix. Our transition matrix we fill with probabilities, and that's an m by m. Need to perhaps pop that in at the top. It's our m by m transition matrix, and n represents the number of the step n. So this is step n. And when we talk about step, it's really referring to, this is our starting point. Step 1 would be our next day or next attempt or whatever it is that we're looking at, and this is the nth attempt. Okay, so that's a very simple simple formula, if you like, using matrices to work out probabilities of events in the future. And so what we might do is just have a look at question. I'll just make one more note here actually. This S0 can be, this can be in the form of a probability. Can be a probability as a percentage or a decimal, which is what we've been looking at here. This is a decimal, but it can also be numerical, or it could be a 0-1 success fail, or 0-1 success / fail. So it could be in that form, this matrix here, and we'll have a look at some examples in 11D as we go. But I'm going to just to keep this as brief as possible, I'm going to work on question 5 just so that we can get started here. So exercise 11D, question 5. This is on page 339. You might just have a little read through that and pause this while you just get the hang of the question. Okay, so back with it on question 5, and that is we're looking at 2 swimming pools in a resort complex, one indoor and one outdoor. So I'm going to say my top row is the probability of an indoor session, and the bottom row is the probability of an outdoor session, and that will be the nth step. This is my transition matrix, which is going to be the probability indoor follows indoor. So most people tend to go back to the same pool each day, but there is a probability of 0.13 that a person who goes to the indoor pool one day will go to the outdoor pool the next. Well, that means that it's a 0.87 probability that they'll go to the indoor pool after going to the indoor pool the day before. The probability that they'll go to the indoor pool having gone to the outdoor pool is, I think it says that, and a probability of 0.23 that a person who goes to the outdoor pool on day 1 will go to the indoor pool the next day. So I've got 0.23 over here. I know that I can fill down to 1. So that's my transition matrix. My step 0 matrix. So at step 0, we've got which is Monday, I've got 60% of people are in the indoor pool, and I've got 38% of people are in the outdoor pool. So there we have it. This is my transition matrix. This is my S0, and this is my Sn. Now, all we need to do now is work out what the question's asking. I'm just turning the page. Find the estimated percentage of people at each pool on Wednesday. Give your answers to one decimal place. So on Wednesday, now this was, so S0 is, I forgot to take note of that, I think it was Monday. Yep, this was Monday. So S0, which is Monday. So on Wednesday, our power n is going to be, so 0 on Monday, so that would mean that S1 was Tuesday. and that S2 is Wednesday. So that means that we're going to raise this to the power of 2. It's going to be the power of 2 because this is going to be S2. So into our calculators goes 0.87, 0.23, 0.13, 0.77 to the power of 2 times 0.62, 0.38. Now I think if you put all that through, you will find that S2, if I go to therefore S2 is equal to 0.63, there goes 1152, 0.368848 if you look at that. So in the estimated percentage of people at each pool on Wednesday, so therefore indoor will equal 63.1%, and outdoor, indoors our top line, and outdoor is 36.9%.